Now we're going to take a look at sampling models. And for now, our joke is the ends justify the means. And that will become more apparent what that play on words means as we move through our lesson. So before, when we're looking at behavior, when we're looking at samples, we were looking at one data point, and if it was unusual. In our examples here, the probability of finding 3 band students in a single class, the probability of a student scoring more than 90 on a multiple choice quiz. All right. Now we're going to take a look more at the averages of samples. So we're looking at the entire sample instead of the individual data points in the sample and how those means or statistics are behaving. So the question would change to the probability that the average of classes you survey will have 3 band students, or the mean. The probability that the mean score of a student on a multiple choice quiz is a 90. So when we're dealing with this, behavior or statistical measures, we usually use the word sampling distribution. The distribution of all values taken by a statistic in all possible samples of the same size from the same population. So just to refresh, population versus sample. Population, we have a parameter like mu for mean, and variance would be, the sigma. Although sometimes you'll see us use it with a little p bar, and on your math chart it will kind of look like that. So you might not see this x bar, but you'll see this x bar next to the mu to tell you that we're talking about the statistic instead of the parameter. You might see SD as well for variant, for standard deviation or variance, instead of S. Now, we make inferences about parameters using statistics because rarely can we measure the actual mean or the actual variance unless we do a census or we're looking at everyone. Statistics can vary from sample to sample. But parameters never vary because when we do the parameter, we are doing the entire population, so we would know the answer. Unfortunately, that's a luxury, and so we rarely know the parameter exactly. Now let's take a first look at proportions. And what is a proportion? It's the fraction of a population that meet the criteria. So that's what we mean in statistics. It's categorical by nature. It either meets a criteria or does not. So we're going to be counting the number of items in our samples that meet certain criteria. And here's some examples of proportion problems. Percent of flips that are heads. Percent of drivers that are speeding. Percent of students who are in band. So it's basically a binomial distribution. So this might bring back some memories to you, where we could calculate the mean and the standard deviation, NP and square root of NPQ. So let's take a look again at that binomial distribution. I'm doing one variation, and basically here, instead of having number of heads, I'm doing proportion of heads. So that's the only thing I'm changing. So we're flipping a coin, and you can see there's the heads and the tails, and I flipped it again and again and again. Now you're not really going to see it until you see, now I'm trying to simulate 1,000 flips. And you're starting to see that it's taking a familiar shape. And in fact, when I showed the distribution, that should look familiar. That's like a normal distribution. The only time it gets away from normal is when n times p is too small, when it's less than 10, or n times p is too large. That would be n times q. So n times p is too large, which would mean n times q is too small. So remember, the binomial distribution behaves like a normal distribution under the proper conditions. That is that NP is greater than 10. I really should say greater than or equal to. Let me do that. And 10. Greater than or equal to. And remember, that came from our 3 sigma work in that unit. And the sample is less than 10% of the population, and the samples are independent. That's kind of, samples being independent is kind of for all the work we do. Now let's take a look at the mean for the proportion. So the old mean on binomial probability, which was the mean of the number of heads you would get or whatever, would be n times p, where n is the sample size and p is the probability of success. But for a proportion, we have to divide by n to get the fraction meeting the criteria. What do we mean? Well, I'm going to say p hat is going to be the proportion of heads, where x is going to be the number of heads, and n is going to be the total number of flips. Well, remember when we studied how statistics change when we do some sort of operation? Here we're taking our old mean and just dividing it by n. So I'm going to write this: the mean of the proportion, or the average fraction, will be the mean of the number of items meeting the criteria, number of heads, divided by the total number of flips. But I know that that's just n times p. So these two n's simplify, and I get the mean of the proportion is just the same as the probability of success. P hat, you notice I'm using that there. That is the statistic of the observed proportion. So that's like what we're actually measuring, kind of like y hat when we did linear regression. P is the parameter representing the probability of success in the population. So that kind of makes sense, that the average fraction of heads you'll get represents the probability of heads that you'll get. All right. It gets a teensy bit more complicated, but not much, for standard deviation. So the old standard deviation for binomial probability was n times p times 1 minus p. That's what's on your math chart that you'll have when you take your AP test. Or we typically just say square root of npq. N is the sample size, p is the probability of success, and q is 1 minus p. Now, for the standard deviation of a proportion, we have to remember, how do we find a proportion? Well, we take our observed values, right, and we divide by n. So since this is just we take our sample, one sample, divide by n, the size of the sample. Since it's pretty straightforward, we can just divide the standard deviation by n, which I did here. So it's going to be the standard deviation of the number of successes divided by n. And here I put square root of npq, all right? And you can see that there's n. And I'm going to actually move the n inside of the square root. When I do that, I have to square it. These two n's are going to simplify. So that, oops, there's a typo. That always happens. That should be p times q all over n. And I don't know how that happened. P times q all over n. I thought I fixed that. All right. So that's actually the formula right there. Okay, and luckily it's correct on your math chart. So if you look at it here, this is the part in the math chart you'll see. So it says if x has a binomial distribution with parameters n and p, the proportional statistics are under this binomial distribution section. All right, the mean of the proportion is just the probability of success, and then the standard deviation is p times q divided by n, take the square root. Now, don't forget to consider some of your assumptions. It should be a simple random sample, or at least no bias. Remember, there are different ways to take samples to minimize bias. There should be independence between samples, just like almost everything we do, unless, we're looking at conditional probability. Some of the conditions, we want the large counts, that n is sufficiently large. So you saw in the binomial distribution, the more flips I did, the more it looked like a normal population. I also want NP is greater than 10 or equal to, really, and I'll put that greater than or equal. And NQ is greater than or equal to 10. And also, I should not take a sample that's more than 10% of my population. All right, the 10% condition. So of all cars on the interstate, 80% exceed the speed limit. What proportion of speeders might we see in the next 50 cars? So first of all, let me pull up my formulas for my math chart. And I can tell that my mu of my proportion is 0.80 and n is 50. Some of my assumptions: start writing down what you're assuming and what the conditions are. When you do your free response, you should be able to do this every time. So I'm gonna reinforce it with the examples here. Assumptions: speeding is independent. It's a simple random sample, or at least no bias, so there's some randomization going on. We want to check our conditions. Is NP greater than or equal to 10? Yes, it is. It's because 50 times 0.8 is 40. 50 times 0.2 is 10, so we're okay there. N is sufficiently large at 50, so we feel pretty confident about that one. And 50 is less than 10% of the population. So start writing these conditions down so you're prepared to write them down on your AP test, or my test for that matter. All right, so now let's go ahead and actually start crunching some numbers. So the standard deviation is PQ over N, or I have the math chart formula there too. I substitute my numbers in, and I basically get it's about 0.057. Now they say, what might we see in the next 50 cars? So the best thing to do is to go ahead and draw a normal distribution. So it's going to have a model. Our model will be approximately normal with a mean of 0.80 and a standard deviation of 0.057. So it's going to look something like this. Proportion of speeders in 50 cars. All right. And so what does that mean? How do you write this as a sentence? According to the normal model, we expect 68% of the samples of 50 cars to have proportions of speeders between 0.743 and 0.857. So you can see these are kind of the words. Let me go ahead and do my pointer highlighter. So proportions of speeders, these are the words that kind of change on this sentence. And then after that, it gets pretty, bullet, points. So it's kind of uniform. So we have proportions of speeders between 0.743 and 0.857. We have 95% should be between 0.68 and 0.914. And 99.7% should be between 0.629 and 0.971. We'll go ahead and look at another model for another example for voting. We don't know it, but 52% of voters plan to vote yes on the upcoming school budget. We pull a random sample of 300 voters. What might the percentage of yes voters appear to be in our poll? So it's not like a specific, what's the probability, give me a number. They're going to want a model. So let's go ahead and we're going to use these formulas again. We know that the mean would be about 0.452 because they gave it to us, and N is 300. Our assumptions: the votes are independent. We hope so. It's a simple random sample, or at least no bias. N times P is 156, no problems there. N times Q is 144, no problems there. N is definitely large enough. And 300 is less than 10% of the population. Now, sometimes you might have some elections where that's pushing it close, but we're assuming that more than 3,000 people will vote in the election. So that might be worth saying. All right, so let's go ahead and crunch some numbers. Let's find the standard deviation, which is P times Q divided by N. So I substitute in the numbers 0.52 times 0.48 divided by 300, and I get about 0.029. So my model is a normal. See how I write N parentheses, you put your mean and your standard deviation, 0.52 and 0.029. And I have a beautiful bell, I always call it a bell curve, but the normal distribution drawn here. And with the different, 1 sigma, 2 sigma, and 3 sigma values. And then I could describe it in multiple sentences here. According to the normal model, we expect 68% of the samples of 300 voters. Notice how I included the sample size in there. All right, that's kind of important. To have proportions of yes voters. So we notice how we're saying yes voters and we're saying proportions between 0.491 and 0.549. 95% of the samples to have proportions between 0.462 and 0.578, and 99.7% of the samples to have proportions between 0.433 and 0.607. Okay, one last example for proportions. So sometimes you might say, oh, what's the probability of this or that? Because right now, so far, I've just been describing some models. Now I'm going to go ahead and apply it using probability. So according to U.S. News and World Report, and I pulled this one off of the Penn State Statistics website, which is an excellent website, by the way. You should be able to get to it. In the population of 4,361 students enrolled in the Penn State World Campus bachelor's degree programs, 811 have military experience. If we were to randomly select 75 students to participate in a research study, what is the probability that at least 25% of the sample would have military experience? So let's go ahead and calculate a mean. This is what we think our, well, actually we know our parameter in this case because they have done a census. So they know this. I presume they did a census. All right. And our sample size is 75. And we're trying to find the probability that our proportion is greater than 0.25. All right. Assumptions. Our samples are independent. And we used a simple random sample or at least no bias. For example, we don't pull 75 students from some sort of military class, or maybe history, or history class might have more military, or a government class might have more military. You want a simple random sample. Check your conditions. Is n times p greater than 10? It's 13.95 and 61.05. And it being at 75, and it's definitely sufficiently large. So it looks like we've met all the conditions with our assumptions. All right. I'm sorry, I forgot to. And 75 is less than 10% of the population, which is 4361. We happen to know the population size in this case. All right. So now let's go ahead. And since we've checked our assumptions and our conditions, we can start to do some work. We'll go ahead and use our formula, P times Q over N, right? And we find our standard deviation is 0.0449, all right? So I have my mean and I have my standard deviation. So I'm going to start to create my normal model. So there's my mean and my standard deviation. And what I personally prefer calculating a z-score every time. Now, I know your calculator can generate some data, and maybe if you draw the picture and show everything, that would be good enough. I personally feel much better with a z-score. In this case, I have a z-score of 1.425. Now, you'll notice in this graph, which is from the Penn State website, they actually didn't do the z-score. They just went ahead. They actually have a nice little graphing package. And they said, oh, what's the probability that it's to the right of this? So if you were doing this on your calculator, you would basically say 1.425 to, say, 1,000, the normal CDF, right? Here they have their little statistical package, and it shows a beautiful little decimal value there for the probability of roughly 0.077.